So I'll be giving you a tour of the different things we can do at moderate and high resolution, spectral resolution for directly imaged planets. So I'll define what spectral resolution is in a minute, but basically the fundamental idea is that every molecule, every species in your exoplanet atmospheres have a very distinct spectral signature. It's like a barcode, but the same way that you can't read a blurry barcode, you kind of need a high spectral resolution in order to be able to identify very precisely the signature of your molecules. So on the left here, let's see, does this work? Yeah. On the left here, you have carbon monoxide, water, methane around examples around 2 microns. So by now, I mean, you've gathered with talks before, we like to measure spectra of exoplanets in order to study their atmospheres. So in this slide, that's from Everett Naskin paper, really thorough paper on the HY29 planets. In this plot, you have most, I mean, not all, but most spectra, archival spectra for the HY29 planet from B to E at the bottom. And you can see that goes from 1 to 4 microns here. And those spectra are great to measure the bulk properties of those planets, say from the luminosity. If you have an age, you can get the mass. You can measure the effective temperature, probably the surface gravity. But abundances might be a little trickier, and I'll talk about this in a minute more. And the challenge comes from 2 places. There's, I mean, we talked about calibration, that can be a challenge, but the spectral extraction we've talked about yesterday too, if you have residual speckles or things like that, can lead to inconsistencies in the spectra. For example, you can see in C here, you might get spectra that don't look always perfectly consistent. Also, atmospheres are complicated. So we have to make simplifying assumptions when we build our models. We might not be able to afford varying as many parameters as I would like, or we might not put the exact correct cloud prescription, for example. So all of that leads to some inconsistencies, sometimes in measured abundances, for example. So this is a lot in this slide. We're not going to go through all of it. The point is, these are all the C2O, so carbon to oxygen ratio estimates from literature and from Everett's paper for the HY29 planet. So from B to C, top to bottom. I'm just going to highlight one, for example, and you can see depending on which study you look at, which models, which data set you look at, you might get values of the C2O that goes from less than 0.3 to 1. So that's not ideal. It's not an isolated example. For example, for 51 Eridani B, also different spectra from different planets producing slightly different spectra, and that leads to slightly different. I mean, I actually forget if they're using the exact separate spectra, but you get different studies that also find different C2O measurement. So we have a tool, another tool that we have for studying direct imaging is higher resolution spectroscopy. And so, what is the spectral resolution? So the spectral resolution is defined as the wavelengths. So it's the OR at the bottom here. It's defined as at the wavelengths divided by the width of a spectral line. So it can be an emission line or an absorption line. And so the higher the spectral resolution, the smaller the feature you're going to be able to resolve. And the smaller the resolution, the broader the feature you can resolve. So you at some point, you'll just get the continuum of the spectrum. And so at the top left here, you have a water template, so a molecular template for a water molecule, and varying the different resolutions. And you can see that above a resolution of about 1,000, you start resolving the fine absorption features of water. And so on the right, you have the same thing for carbon monoxide, around 2 microns. And we can use the fact that at high resolution, we can resolve those molecular features to disentangle the signal of the planet from the signal of the star. And that's because the spectrum of the planet looks nothing like the spectrum of the star. So to illustrate that example, I'm going to take a moderate resolution spectrograph. So here's going to be Osiris at Keck, so resolution of 4,000. And let's say it's an integral field spectrograph. So you get a spectra. I mean, you get a non-zero field of view here, and you get a spectrum at each position in the field of view. Rob talked about going from here to as the magic step. You build a spectral cube. And the point is that before you do any data processing, what you'll see is just a stellar glare. You see starlight everywhere. And if I plot the spectrum at each position in this little field of view, you'll get all these gray curves here at the bottom. And the speckles are going to look like a wavy thing. But the important thing here is that the waves are pretty low frequency. They are like slow waves, but the molecular features. So here you have the example of a template for H109C. Here you have carbon monoxide and you have water a little bit throughout. Those features are at much higher frequency. So what we can simply do is smooth all the spectra in your cube, remove the continuum, that's called high-pass filtering, and then you basically remove the starlight everywhere. And at this point, you might tell me, and you'd be right, but wait a second, you should probably have, I mean, this is a ground-based telescope, you're going to have telluric lines. Also, the starlight has stellar feature of its own. The point is, we can calibrate those. You can, I mean, if you can go to a calibrated star for calibrating the tellurics. Because we do direct imaging, the planet is spatially separated from the star, so we can also get a spectrum of the host star that doesn't include the planet signal. So then you can use those calibrator to either you divide the tellurics from your data, or you multiply it to your model. There's different data reduction technique. I don't have time to go through them in this talk, but the point is we can manage that. And so, yeah, so once you have the high-pass filtered spectra, which are at the bottom, where you have your features of water and carbon monoxide, the next step is to combine all this molecular features across the entire wavelength range. And we do that with something that's called cross-correlation or template matching or match filtering. Those are all the same things. And because any individual lines might not be able to detect any individual line, but if you look at the aggregate, at all the lines combined, that's when you're going to be able to detect those molecules. So that's what, for example, Queen Konopaki did in 2013 on that planet at H109C. So you have the high-pass filtered spectrum at the top, and you can take some molecular template. So here you have water and carbon monoxide, and we'll see how well it fits the data by shifting those models. So you start from left and then you move it. And when the molecular features of the model align with the molecular features of your data, then you'll get a peak in the best fit amplitude. So that's called the cross-correlation function here. And so because you see a peak for carbon monoxide and water, you basically detected those molecules at high spectral resolution in the spectrum. This was moderate spectral resolution, so 4,000. If you go at even higher spectral resolution, so this is going to be 100,000 with another instrument called Priris at the VLT, and that's worked by Ignace Snell in 2014. And you place this is not an interpolation spectrograph. This is going to be a slit spectrograph, and you place a slit across your star and your planet, and then you run the same technique, the cross-correlation function, at each position in your slit. Well, then you'll see that you'll detect the planet at this, you're not going to see any signal at the position of the star, but you'll see the planet at its own separation and radial velocity here. And then you can combine then you can look at the cross-correlation function of that planet here. And because it's such high resolution, you can actually notice that the cross-correlation function here is wider than what you would expect from the model in the dashed line. And that's because the planet's spinning. So you get, it's rotating. So one half of the planet is blue shifted, one half of the planet is red shifted. So you get a broader cross-correlation function, and you can measure the width and derive the spin, which measures as a V sine I, so 25 kilometers per second here for beta pictoris B. I just want to mention this, although I'm not going to talk about it in the rest of the talk, is that there's also a broad body of work to apply high-resolution spectroscopy techniques to short orbital period planet transiting or not necessarily transiting. But the point is, for those planets that orbit their star in like only a day or so, the radial velocity of the planet moves so fast that it actually changes over the course of the night or like a couple hours. And if you look at the cross-correlation function here, so you have radial velocity at the bottom as a function of time. I mean, it says phase, but like you can think about this as time. You can see the radial velocity of the planet that changes by looks like 100 kilometers per second over the course of this observation. And that's great because you can actually use that information to see like the lines that don't move belong to the star and the Earth, and the lines that do move probably belong to the planet. We can't do that with direct imaging because the planets are so far away that over the course of you might need to wait years or even decades in some cases in order to see any variation in the radial velocity. So this is great, but we can't actually use that for direct imaging. So before let me check how I'm doing on time. Yeah, before I dive into the science cases, just to give you an overview of the kind of spectrographs that we might use. So Rob talked about integral full spectrograph earlier. So we do use those. So the advantage of those is that, yeah, you can get a spectrum over a non-zero field of view that can get to a few arc second across. But because your detectors have a finite size, you can't, well, I think there's some project to build some of those, but typically they're going to be moderate spectral resolution. Then if you want to go at higher resolution, you can think you might have your traditional slit spectrograph. So that was, for example, for beta Pictoris, the result I just showed that was slit. But nowadays, there are a new generation of instrument of high resolution spectrograph that's like optimized for high contrast imaging and direct imaging of exoplanets, and they tend to have what we call single mode fiber. Sorry, I'm losing the pointer. Okay, here we go, over here. And because one of the downsides of the slit is that, well, the throughput, so you're going to get a lot of light from the planet typically, but you're also going to get a lot of starlight because there's no filtering. The single mode fiber is so a fiber that you need to place exactly at the position of the planet. And the advantage of this is only light that looks like, that looks like a point spread function, like a Gaussian-like spatial profile is going to enter the fiber, but speckles that might not exactly look like that will not enter the fiber as well. So you get some starlight suppression in this way. You also get more stable spectra typically with a fiber. So new generation of instrument tend to adopt this architecture. Okay, so what can we do? So I showed like the seminal papers that started this a few slides ago, but what other things we can do with a moderate and high resolution spectrum? I might stop saying moderate and high resolution spectrum. I might just say high resolution spectrum, just probably assume moderate to high. So these are, I think, the main things we can do with that kind of spectra. And I'm just going to go through each of them one by one. I'm going to start with the radial velocity, which I've mentioned before. And the idea is, because we can see the molecular lines, the spectral lines, by measuring how shifted they are, then you can measure how fast the planet is moving towards or away from you. Equivalently, that means measuring basically the position of the peak of the PSF, of the system, not the PSF, the peak of the cross-Gaussian function at the bottom that's going to give you the radial velocity of the planet. So what can we do with this? Well, actually pretty straightforward. The one thing we can do is like better characterize the orbit of those planets. So especially for planets that are very far away, that don't move very quickly, having an extra point that tells you the third dimensional, like the velocity in the third axis can be helpful. And that's the case for HG1160b here, where Clarissa do. And with that, the radial velocity measurement, you can see the preferred orbit had a very high eccentricity. But if you add the radial velocity measurement, then it actually prefers the low eccentricity orbits are preferred. And that's important because we actually like to measure eccentricity for the whole planet population, because that's going to actually tell us how planets form too. And for that, I'm not going to dive into it, but I'll refer you to the work by Brendan Bower and all the new paper by Clarissa as well that talks about this. Another thing we can do with the radial velocity, and that's something I'm personally pretty excited, I think is pretty cool, is measuring exosatellites. They're trying to look for exosatellites. So you all know, maybe, but you might have heard that we can detect exoplanets around stars by measuring the radial velocity of the star. And if you see a wobble in the radial velocity of the star, that means that you have probably a planet that tugs on it. Well, now that we can measure the radial velocity of the companions themselves, then you can look for a companion to the companion, and now you might be able to look for an exomoon or exosatellite. And so this is an example for GCLUB B, so low mass brown dwarf, and with a new instrument called, not so new anymore, but an instrument called KPIC at Keck with a resolution of 35,000. So Caitlin in the room was able to measure the radial velocity of that companion over like 11 different epochs. And by combining all of that, we are sensitive to satellite down to a mass ratio of about 1 to 3% at the separation equivalent to the Galilean moons in the solar system. So yeah, you have mass ratio here and separation in Jupiter radii at the bottom. So that's not quite deep enough yet to be able to detect like the small satellites like the Galilean moons. We tend to have mass ratio down into a 10 to the minus 4. But with the next generation of instrument like HISPEC, that's like, or the next generation of telescope with the extremely large telescope, that's probably going to be possible. So now the spin. Now, we've talked about this about beta pictoris B. So by measuring the width of the spectral lines or the width of the cross-correlation function, you can measure how fast a planet is spinning, because one side is blue shifted, the other side is red shifted, so it broadens the line. And again, the result from Ignace Snell in 2014 for beta pictoris B, I mean, we didn't get a lot of high contrast companions in the meantime, but now with a new generation of high contrast, high resolution spectrographs, that becomes pretty much routine. And so, for example, there was a paper, Jason Wang, measuring the spins of all the HLS9 planets. I'm struggling with the pointer. Yeah, so the HLS9 planet here and their spin here in kilometer per second. And same, a little bit like eccentricity, we like to measure the spins of all companion, like high contrast companions, because that's going to say something about how they formed. And for example, there's the idea that the spin of a planet depends on like its early interaction with its own circumplanetary disk that might slow it down. I'm not going to dive into the detail, but I think the current measurement are consistent with that idea of magnetic braking. I'm going to refer you to work by Marta Bryan, who has done a lot of this, if you want to dive in more detail in this. So now Doppler imaging. So that's an interesting one, because I think we're all excited about this, but there's actually not that many results. Maybe I should go back, actually, just one sec. So the idea of Doppler imaging is if you have a cloud or a dark spot that is on the top, I mean, at the surface of your planet, then it's going to make the blue side a little dimmer for a bit, and then once the cloud is on the other side, it's going to make the red side a little dimmer. So it's basically going to change the shape of your spectral line in your spectrum, and that, as a result, also change the shape of your cross-correlation function. And so that's what Jan Crossfeld did in 2014 for the closest brand dwarf, Lumen 16b. And on the left here, you have the deviation from your average spectral line, and you can see there's a dip that moves with time. Like time is the y-axis, radial velocity is the x-axis. So you have that dip that moves across as the brand dwarf is spinning, and that corresponds to a dark spot on your on the surface on your brand dwarf that moves around. And so I think that's really cool, but the problem is you need really high signal-to-noise ratios to do this. You need bright objects, and you need very good calibrations, Rob said. So I hope there's going to be a lot more of this in the future, but like for now, this is basically your seminal paper, and there's more work needed on or there's a simpler and Beth Biller here for maybe we're like looking at variability of the line, maybe not looking at the shape, but just that the variability of the object is an interesting thing. There's some studies on that. I should have mentioned it, but the next thing is going to be atmospheric characterization. So by measuring the depth of the lines, for example, the relative depths as a function of wavelengths between different molecules, then you can characterize your atmosphere and measure abundances. And from the ground at K-band, so around 2 microns, you have that carbon monoxide bandhead, so like very clear feature of carbon monoxide here, which are great to measure, for example, that carbon to oxygen ratio that we talked about earlier. And so this is an example for Kappa Andromeda B. And you can see that that constrains the C2O ratio very well, because you can clearly see which of the ones that has the right depth, like just from looking at the depth of the line. And we've been able to do that on quite a few substellar companion at this point, and we've found that they're pretty much all consistent with a stellar C2O ratio. So the reason we care about C2O ratio, because there's some idea that we might tie it back to the accretion of the planets when it forms. So for example, depending where the planet formed in its planetary disk, it might affect the composition. But here you can see that there's probably maybe some trend. At least the transiting planet seems to have fairly higher C2O ratio compared to the direct imaging one. Is that a trend? I mean, we need more planets at directly imaged planets as smaller masses, I think, to conclude further. Something very exciting too, beyond those like classical molecules like carbon, oxygen, I think it's looking for isotopologues. And that's where higher spectral resolution can shine even more is for those molecules, you get different isotopes. For example, the carbon, instead of 12C, you can look at for 13C. And so this is work pioneered by Yapeng Zhang, 2021, around this planet, 2YC4 number. But when you fit all the other molecular features, you can see that in residuals, you see that detection for that isotopologue. And that might be a better tracer of planet formation. Again, I'll refer you to Yapeng's paper if you want to dive into the application of the science cases here. And those are becoming a lot more common. For example, there was a recent paper using Jean-Baptiste spectra of VHS 1256b, and you can see like very clear detection of isotopologues using a moderate resolution spectrum, so resolution 2700 here. So 3 different isotopologues, pretty amazing. And at even higher spectral resolution from the ground, this is work by Jerry here, Sean, you have, we've like been able to double the number of like isotopologue measurements. So it's still the beginning, we're still starting, but I think this is an exciting path for the field here. Because currently there's no like specific trend identified, but we're just starting. But last but not least, planet detection. So moderate and high resolution spectroscopy is not just for characterizing known planets. There's actually a good case to be made for as a detection tool. And the first example is actually from Sebastian Haffer, who gave the talk this morning, the detection of PDS-70C. So funny enough, this is not actually using the cross-quotient function that I was talking about earlier, but just by using the fact that you have a high enough spectral resolution to resolve the H alpha emission line in the visible. Well, that means you can detect planets that are still accreting. When you have accretion, you get an H alpha emission. And that's how Sebastian detected PS70 here, which is a really cool system because those planets are like literally still forming, still accreting material. This is actually my work. But trying to make the case for planet detection using high resolution spectroscopy techniques, because we're less sensitive to speckle variability, because we can use that high-pass filtering thing where we can just remove all the starlight and it doesn't matter if it varies, it doesn't matter if it's chromatic. Well, that means we can actually go pretty close in. We don't need to rely on angular differential imaging like ADI, SDI, that kind of things you might have seen yesterday. So that means we can go pretty close in and be pretty much photo noise limited. And for example, using JWST, we showed that we might be able to be more sensitive than the chronographic mode on JWST with that, with an integral spectrograph and the higher spectral resolution. So at even higher spectral resolution, there's some cool techniques. I think I'm going to have to go quickly. I'm running out of time, but there's some ideas of combining, I mean, not some ideas, we're demonstrating them now on the telescope, but of combining, for example, a vortex chronograph with a single mode fiber, and that's called vortex fiber nulling. And the idea is that you use the combination of both to create an annulus of sensitivity where it's like within the full F max of UPS, the spatial resolution of your telescope, so you can get really close in, like 40 milliarcsecond here. So people, Dan Eshery is working on this. So for the thing about the future, I mean, I'm forgetting a bunch, but just a couple of things I'm excited about coming in the next few years. All those JWST spectra that JWST provides a moderate resolution spectrum from 1 to 20 microns. So this is the spectrum for VHS 1256, incredibly rich spectrum. So we can take years for us to analyze all of that. And we should be able to get something maybe not as good, but close to that for most of our directly imaged planets. Also, I think those high resolution spectroscopy technique is going to be even more powerful once we get to the even bigger telescopes. So we're building the extreme, I mean, not we, but Europe is building the extremely large telescope. And we should be able to detect Earth-like planets right nearby M stars. So maybe using the high spectral resolution to detect biosignatures. I think that I just proposed. I think exosatellites would be pretty cool. So looking forward to that. And I'm going to leave my conclusion slide in there, summarizing all the things we've talked about. So radial velocity, spin, Doppler imaging, atmospheric characterization, abundances, and detection. Thank you.
Okay, thank you, Jean-Baptiste. Questions? Let me run this up here. I'm going to go up there first.
Thank you for the presentation, Sam. I wonder what order of magnitude of precision can we determine relative abundances of major gases, like 3-5 most abundant gases in exoplanet atmospheres, like what fraction of atmosphere with respect to each other each gas takes, like quantitatively, what is the of magnitude of precision?
Sorry. And the typical uncertainties that we get, for example, the carbon to oxygen ratio is going to be about 0.1. So 0.55 is the CTO ratios of the sun. So we typically get measurements of like with uncertainty just 0.1 on our planets. You'll see if you go back to my slide, you'll get much smaller uncertainties, but they're typically the statistical uncertainties that don't include, for example, model uncertainties or all kind of uncertainties that we don't know about. But I would say that I would trust uncertainties about around 0.1. For metallicity, probably about the same. But 0.1 in logarithm in that case, because metallicity measured in log. Yeah. So 0.1 in log is why is that? Maybe closer to a factor 2 in uncertainties. Well, less than that. I don't know. I can't do logarithm in my head right now, but someone can tell me.
Great talk, Jorge Sanchez, Arizona State. You give a great overview of the benefits of modern high resolution spectroscopy. We've heard a lot this week about the benefits of different kinds of spectral resolutions and low to moderate to high. I'm wondering what your thoughts are on the sort of prospects of combining different spectral resolution instrument or different data together. What can they sort of offer each other? How can they complement one another? What can we get out of that?
Yeah, I mean, they tend to be all complementary because they have different limitations. So, for example, a lower resolution tends to be pretty sensitive to speckle residuals, but we tend to lose. I mean, for now, every high resolution spectroscopy study for exoplanets removes the continuum, so we don't have the continuum of the spectrum. So combining both is kind of almost necessary. So you get, I would say, you can get very good bulk properties from your low resolution spectra and photometry, but for the abundance, I would tend to go towards a higher spectral resolution because then you get a better handle on each individual molecules if you can. I mean, sometimes planets are too faint, but.
Hi, Sam Walker, University of Hawaii. I was just wondering, for the detection of exoplanets using high resolution spectroscopy, what sets the contrast limits and what prospects there might be for improving that?
I mean, it's like with every technique, what sets the limit or the whatever systematics limits you. So it's a good question, but it's also a hard question because it depends on the instrument, it depends on the resolution. I mean, from the ground, we might struggle with telluric variability a little bit, depending on the instrument. For example, for the single fiber one. I mean, with jet I'm struggling with the extraction systematics, the undersampling of the detector but I tend to think that the higher spectral resolution is because it doesn't care as much about the speckle variability, tends to be closer to the photo noise limit, especially, which is why it gets really good. It's basically good when you're speckle noise limited. When you're struggling to subtract the speckles for any reason, that tends to perform quite well.
Last question, please.
When you're trying to measure the spin of an exoplanet, do you have systematics from different lighting from the star on one side of the planet versus the other that could masquerade as a radial velocity?
So you mean the combination from the stellar spectral features?
Yeah, so the stellar lights one side more than the other, right?
Like I mentioned, we tend to model those pretty well because we can in all cases get an empirical model of that star. So it's not like we rely on models to get the spectrum of the star. So it is the star, and either taken at the same time if you have an integral spectrograph, or you go back between the star and the planet if you have like a fiber or a slit. So we have a perfect, as good as you can get model of the star. So I don't think it typically contaminates, or at least I have no evidence to show that the stellar light contaminates or biases anything in that case. Thank you.
Okay, thank you.